Okay, so the only operation we haven't spoken about when it comes to matrices is division. But we don't divide matrices. What we do is we find their inverses. Now, here's something very important. Before I talk about finding the inverses, I need to speak about what's known as the identity matrix. First and foremost, the identity matrix is a square matrix. Did you catch that? It's a square matrix, which means it has to have the same number of rows as columns. For example, a 2 by 2, a 3 by 3, a 4 by 4, etc. Got it? Okay. Now the identity matrix looks like one of these, or like I said, a 4 by 4, 5 by 5, etc. There's ones on the diagonal and zeros everywhere else. Ones on the diagonal and zeros everywhere else. That's the identity matrix, and it is always a square matrix. We use the identity matrix to find the inverse of another matrix. Now, here's something that's also key. If the identity matrix is a square matrix, and I use it to find the inverse of a matrix, that means the matrix I'm trying to find the inverse of must also be square. Got it? The matrix I'm trying to find the inverse of must also be square. If I'm going to use a square matrix, then I need a square matrix to find the inverse of. If it's not a square matrix, it's not going to have an inverse. Got it? Okay. So, in this particular problem, it is asking me to find the inverse of matrix A. Now, gratefully, matrix A is a square matrix. It's a 2 by 2, right? Here is your setup. You are going to set up matrix A to complete the setup. Right next to it, you are going to set up the identity matrix. Ones on the diagonal and zeros are everywhere else. And your goal is to do Gauss-Jordan elimination on this. Your goal is to, on the left side, the original matrix, your goal is to get ones on the diagonal and zeros everywhere else. And as you do the operations to make this the identity matrix, over here turns into the inverse matrix. Now, some matrices don't have an inverse, and I'll show you what happens with those. But understand, this is your setup. I have a square matrix, and right next to it is the identity matrix of the same size. My goal is to make the original matrix look like the identity matrix using Gauss-Jordan elimination. And as I do that, this side is going to turn into the inverse. With me? Okay, so stay tuned. I'll be right back to work out that. Okay, so let's finish this problem off. Let's find the inverse of matrix A, which is the matrix on the left side. Remember? I'm just going to perform Gauss-Jordan elimination, which means the first thing I need to do is I need to identify the main diagonal. It has the numbers 3 and 4 on it, and my goal is to get all the numbers below and above to be 0. So remember, in a previous lecture we went through how to do this. Go back to that previous lecture if you need to remember how to perform this. Because remember, this is called Gauss-Jordan elimination, which means it's nothing more than the elimination method. I need the numbers to be the exact same numbers, but opposite signs, so when I add them, they cancel out. So in this particular case, gratefully, the 3's are both the same, but I need one to be negative. So I'm going to take the second row, I'm going to multiply by a -1, and then I'm going to add it to the first row, and my result goes in the second row, because that's where I'm trying to get the 0. All right, so let's take a look and see what's going to happen here as I do the work. Row 2 is the one that's going to change. So we're just going to rewrite row number 1 as is, since I'm not trying to get a 0 in that row. And if you need to do your side work, then get another piece of paper and do the side work. We need to do negative 1 times row 2, and then I add it to row 1. So take row 2, multiply by a negative 1. What do we get? Good. Negative 3, negative 4, 0, and negative 1. And then I'm going to add that to the first row, and when I do that, I get 0, which is what I was going for, a negative 2, a positive 1, and a negative 1. So that is my new row 2. And now remember, we start all over again. We identify the main diagonal. I got all the numbers below the main diagonal to be 0, and now I got to get the numbers above it to be 0. So I need this 2 to be a 0. So, yeah, gratefully this one's quite nice. All I have to do on this one is take the first row, add it to the second row, and the answer goes in the first row position, because these are already the same number and opposite signs, right? Okay, and let's see. Row 1 is where my answer is supposed to be, so I guess I need to do this addition work before I write it down. So 0 plus 3, negative 2 plus 2, 1 plus 1, and negative 1 plus 0. Good. I'm not trying to get a 0 in the second row, so I'm just going to rewrite it. We good? Okay. So now I'm going to identify my main diagonal again. Gratefully, all the numbers above and below are zeros. And so now what I'm trying to do is I need the numbers that are on the diagonal to be 1s. Which means we are going to take the first row, and how am I going to make that 3 into a 1? Good, I'm going to divide the first row by 3. And then I need to take the second row, and yes, divide by a negative 2 in order for that to become a 1. Good? All right, so let's see what we get. 1, 0. Remember, I'm dividing by 3, so this is 2/3. This is negative 1/3. The second row is being divided by a negative 2, so 0, 1, negative 1/2, and a positive 1/2. Agreed? Okay, so notice we accomplished our goal. Our goal was to make this left side matrix to be the identity matrix, which we did. Which means this over here used to be the identity matrix. That's my inverse matrix now. So, since this was called matrix A, right? This is A inverse. And so A inverse looks like 2/3, negative 1/3, negative 1/2 times a positive 1/2. There is my inverse matrix. And gratefully, I'm not using any new operations to do this. I'm going back to what I learned, Gauss-Jordan Elimination, and that's what I'm using to go from the original matrix to the identity matrix. Pardon me, to go from the original matrix to the inverse matrix by using the identity matrix. Good? Okay, now, to check my work, because we should always check your work. I know, we trust ourselves these days, and so we usually don't check our work. But to check it, I would take the original matrix, multiply by its inverse, and it better equal the identity matrix. Makes sense, right? They should cancel out. But it's a two-part check. This is only the first part. The second part is you got to take the inverse, multiply by the original, and it better also give you the identity matrix. You have to check it in both directions. The original times the inverse, and then the inverse times the original. And in both cases, you better get this identity matrix back. That's how you check your work. Cool? Okay, hang in there. Got a little bit of a larger matrix we're going to find the inverse of. All right, so let's look at problem number 2. They ask us to find the inverse if possible. But remember, in order to find the inverse of a matrix, this needs to be a square matrix, doesn't it? Is it? Yeah, it is. It's a 3 by 3, so it's a square matrix. So remember, we have to set up the identity matrix right next to it, don't we? Okay, so for the interest of board space, I am just going to erase this bracket, and I am going to set up the identity matrix right next to it. So when I do that, my identity matrix, remember, has 1s on the diagonal and 0s everywhere else. And my goal right now is to get the matrix that's over here on the left to look like the identity matrix. And as I do the work, the left side the right side matrix turns into the inverse. Good? Okay. So remember, nothing but Gauss-Jordan elimination, so we have to remember that. And if you need to go back and look at that previous lecture, please make certain you do that. So identify the main diagonal, and I need to get everything below it and above it to be zeros. So the first numbers I'm getting zeros are what? Yeah, the 2 and the 6. Agreed? Okay, so, and remember, I have to use this number 1, because it's on the main diagonal. So I need these two numbers to be the same but opposite signs. So what are we going to do? Remember, it's elimination, which means I need them to be the exact same number. Yeah, that means that needs to be a -2, doesn't it? So, okay, take the first row, multiply by -2, add the second row to it, and my answer goes in the second row spot, doesn't it? So let's see what it looks like. First row is not changing because I'm not trying to get a 0 there. I'm trying to get a 0 in the second row. So the first row is just going to remain the same right now. Now, second row, I have to multiply the first one by a -2, and then I'm going to add these two rows together. So gratefully, I've already done my work. You might want to pause the video at this point, multiply the first row by a -2, and then add it to the second row, and let's see if we agree. Okay, hopefully you got your answer. I'm going to get my answer written down here, and hopefully, as I said, we're in agreement. So I have 0, -1, -3, -2, 1, and 0. Did we get the same numbers? Good. So, got the -2 to be a 0. Awesome. But I still need that -6, don't I? Okay, but I can only use this 1. So I need these two numbers to now be the same, but opposite signs. So, good. I'm going to take -6, multiply it by the first row, add it to the third row, and my answer goes in the third row position. Okay, so you need to take the first row and multiply by a -6, add it to the last row, and let's see if you and I agree. So pause the video and do that work. Okay, so I'm assuming you did it and you're back because you've got your answer. So let's see if we agree. So this will be a 0. This will be a -5. This will be a -8. This will be a -6. This will be a 0. And then this will be a 1. Are we in agreement? Good. All right. So we start all over again. We have to identify the main diagonal, don't we? And my goal is to get the numbers above and below to be a 0. So right now I need this +1 to be a 0. So what are we going to do? That's right, we have to use this -1 because it's on the main diagonal, right? We're not trying to get that to be a 0, so that's the number I've got to use. So, yeah, you're like, this one's easy. You're right, it is easy. Because all I have to do is take the first row, add it to the second row, and the answer goes in the first row, doesn't it? Okay, so let's look. So all we're doing is adding the first two rows together. So we get 1 and 0, -2 negative 1, 1, and 0. Do you agree? Good. So do I. I'm checking my work. There we go. And now I'm ready to write the second row, which I'm okay to do because I'm not trying to make that number a 0. So 0, negative 1, negative 3, negative 2, 1, and 0. And now the third row. I'm trying to make this and this negative 5 into a 0, aren't I? Which means these two numbers need to be the same but opposite signs. So what are we going to do? Yeah, I need to turn that into a positive 5. How? Okay, so I'm hearing you say, take negative 5, multiply it by the second row, add it to the third row, and my answer is going to go in the third row position. Excellent. Okay, so once again, pause the video because you need to do this work, and then when you're done, come back and let's see if we get the same numbers. Okay, you're back? Loving it. So here's what I got. I got 0, 0, 7, 4, negative 5, and 1. Right? Right. We good? Okay. Start all over again. Identify your main diagonal. Get everything above and below to be a 0, which means I need these two numbers to be a 0. So, let's see how you're following along. So, to get the negative 2 to be a 0, I need to use a 7, don't I? Yeah, in this case, both of these need to get multiplied because I need to turn them both into a 14. They're already opposite signs, but I need both of them into a 14. So, it looks like I need to take the first row and multiply by 7. And then I need to take the third row and multiply by a 2. And then add them together. And my answer goes in the first row position. Agreed? All right, so let's see if we get the same. Again, pause the video, do the work, and then come back when you're done. Okay, so let's see if we got the same numbers. I get 7, 0, 0, 1, negative 3, and 2. Good? Okay. But I still need to make this negative 3 into a 0 using that 7. So it looks like I have a double multiplication to do again. Yeah, both of these need to turn into a 21, right? All right. Which means I'm going to take that second row and multiply by 7. And then I'm going to multiply the third row by a 3, add them together, and my answer goes in that second row, doesn't it? Okay, pause the video, do that work. All right, you must be back because you started the video again. So here's what I got for the second row. Again, hopefully we're in agreement. I got 0, negative 7, 0, negative 2, negative 8, and 3. Did you get the same numbers? Cool. And then I need to write the third row down. And here we are. So I'm just doing a quick double check with my numbers to make sure I've written everything correctly. And I have. Okay. So I got zeros above and below the main diagonal, didn't I? But now the main diagonal needs to be all ones. Clearly those are not ones. So, just a little bit more. First row, good, divide by 7. Second row, good, we have to divide by negative 7. Third row, we got to divide by 7. Right? Okay, let's see what we get. Pause the video if you want to and then come back. Okay, you must have done it. So here we go. First row, divide by 7. 1, 0, 0, 1/7, negative 3/7, 2/7. Second row divides by a negative 7, 0, 1, 0. That would give me 2/7. That would give me 8/7, and then a negative 3/7. Third row, divide by 7, 0, 0, 1. So I got 4/7, negative 5/7, and then 1/7. Cool? Yeah, this whole inverse is based upon us knowing how to do Gauss-Jordan elimination. So as I said, go back and review that video if you need to. So now, let's finish her off. That means the inverse of matrix B, also a 3 by 3 matrix, because I started with a 3 by 3, would be 1/7, negative 3/7, 2/7 on the first row. Second row is a 2/7, 8/7, and negative 3/7. And the third row would be 4/7, negative 5/7, and then 1/7. Here is my inverse matrix. Good? You're like, those numbers are a little nutty. They're all fractions. They are, which is why you always get the main diagonal to be 1s at the end, so you don't work with fractions as you're going through all of this. Cool? Okay, now, remember, to check it, you would have to take the original matrix and multiply it by its inverse. But you'd also have to flip them around and take the inverse and multiply by the original, and both of those multiplication problems better give me that identity matrix. Good? Okay. Now, you know, the directions said to find the inverse if possible. As long as it's a square matrix, we're able to try to find the inverse. But not all square matrices will have an inverse. You're like, well, how do you know? Here's how you know. And I'm just going to pick one of the matrices I worked with. If you end up with something like this, and I'm just going to pick this one right here. Why? Just because it's right above my head. If you end up with something like this, one of the rows goes to 0, yeah, there's no inverse. Got it? There's no inverse matrix on that because I can't continue my process. Cool? Okay. Now, hang in there because I got another problem, and it's an application of inverse matrices. Okay, so this particular problem is asking me to solve this system of equations by using inverse matrices. I'm going to tell you right now, it's not the best way to solve a system of equations by using inverse matrices, but I want you to see this just so you're familiar with it, because the authors of the book actually show you this, and I want to make certain, as I said, you understand it. Now, here's the deal. We need to set up a matrix, or pardon me, let me back up. I need to make sure that these equations are in the correct format, because I'm going to end up using Gauss-Jordan elimination, which means I need to make sure all the variables are on one side in alphabetical order, and everybody who's not a variable's got to be on the other. So are these good? Of course, they're good. Yay! So I need to set up one matrix for the coefficients. So I'm going to call it matrix A. And matrix A is my coefficient matrix. And then I'm going to set up matrix X, which is my variable matrix. And then I'm going to set up matrix B, which is I'll call it the answer matrix. It's what numbers is actually equal to. So I'm going to call it the answer matrix. Okay? Now, the coefficient matrix is dealing with the coefficients of my variables. With me? It's dealing with the coefficients of my variables. So in this particular case, matrix A is going to have 1 and 7 and 3 and 3. It's a 2 by 2. Good? All right. Now matrix X. Now, this one, I have to make certain you understand why this one has the size it has, why it's the order it has. My coefficients are multiplied to my variables, aren't they? Yeah, the coefficients are all multiplied to the variables. So 1, 7, 3, 3, they're all multiplied to the x's and the y's, yes? Which means these two matrices need to be multiplied together. So I have to remember my rule for multiplication. If this is a 2 by 2 matrix, then this matrix X over here, the first number needs to be what number if I'm supposed to multiply these guys together? Good, some of you remembered. It's got to be a 2. It has to be a 2. Are you with me? Okay. Now, that means, now be careful here. That means I'm going to have an X in this matrix. But this matrix doesn't have to be a square matrix. Remember, I'm supposed to end up with 1x and 7y. So remember, when you do your multiplication, first number times first number, so 1x, and then I take second number times second number. So in this case, if I'm supposed to get a 7y, that means this down here has to be a y. So now I have 1x plus 7y. Does that make sense? I don't need another column because 1 and 7 are only written one time. A 1x and a 7x, which means this is going to be a 2 by 1 matrix. Check the second one. 3 times x, 3 times y. 3x plus 3y. Cool? Okay. Now remember, when you multiply these two matrices together, it's supposed to give me the answer. So if you take a 2 by 2 and multiply by a 2 by 1, gratefully these guys here are exactly the same, which means my result is a 2 by 1, which is exactly what it should be, 11 and negative 3. Okay? Yeah, I know. As I said, it's not the most efficient way to solve these systems of equations, but I'm just showing you that this is one way that inverse matrices are actually used. Okay. Got it? If I take the coefficient matrix multiplied by the variable matrix, I get this matrix. Good? All right. So, let me write that down as a matter of fact. If I take the coefficient matrix and multiply it by the variable matrix, I get the answer matrix. If I wanted to get rid of this A and solve for x, I normally would divide both sides by A, wouldn't I? But since these are matrices, we don't divide matrices. We have inverses to them, don't we? So if I take this side and multiply by the inverse of matrix A, these guys should cancel out, shouldn't they? And if I take this side, I have to do the exact same thing and multiply by the inverse of matrix A, don't I? Okay. On this side, it cancels out, doesn't it? And remember, it doesn't matter the order in which I multiply these two matrices, A and its inverse, they're going to cancel and give me the identity. So I'm just going to be left with x. But the question is this side. Does this side, do I write it as B times A inverse, or do I write it as A inverse times B? Which order can I multiply those matrices together? Remember, Here is your A, it's a 2 by 2, and here is your B, it's a 2 by 1. Remember, A inverse is also going to be a 2 by 2. I showed you that on the first problem, didn't I? So which order do I multiply these? Do I do the B first times the A inverse? Or do I do the A inverse times the B? Yeah, it's this one, because I'll have a 2 by 2 times a 2 by 1, won't I? If I flip it around, you can't do a 2 by 1 times a 2 by 2. It doesn't work. Which is why on this side it is actually written A inverse times B. Cool? Okay. So, in order to solve for the variable matrix, the x and the y matrix, I need to take the inverse of A and multiply it by B. You're like, oh my gosh, I have to find the inverse. You're right, you got to find the inverse, but gratefully I already did it. All you got to do is go check my work. But this is what I got for the inverse matrix, so you go do it and make sure that you agree with me. But here's what I got. For the inverse matrix, I ended up with negative 1/6, 7/18, positive 1/6, and a negative 1/18. 1/6. Yes. And making sure I've got it right. Yes. Good. We good? Okay. So like I said, I did the work already. Here it is. So I need you to stay tuned because now that we have the inverse matrix, we're actually going to be able to do this work. So stay tuned. Okay, I'm back. All I need was a little bit of board space, so I erased this down here so we had some board space to work with. So here we go. I am going to do this work over here. I'm going to take matrix X, which was my variable matrix, and that's going to equal the inverse matrix, which I already have found, and I'm hoping that you worked on it and got the same numbers. And I'm going to take this and I am going to multiply it by matrix B, which was the answer matrix. Right? Okay, so we have to multiply these two matrices over here. So let's see if we're going to be in agreement on how we multiply it. So remember, this is a 2 by 2. This is a 2 by 1. My answer is going to be a 2 by 1, isn't it? So let's see what we get. So I have negative 1/6 times 11. That's a negative 11/6, isn't it? First number to first number, and then I have got 7/18 times a negative 3, which will be a negative 21/18, right? And then I've got 1/6 times 11, which is a positive 11/6. And I add to it negative 1/18 times negative 3, which is a positive 3/18. I gotta do some simplifying here. Looks like a negative 11/6. Gratefully, this fraction will reduce by 3, won't it? So that'll be a negative 7/6. And this bottom one is 11/6. And again, gratefully, this reduces to 1/6, which means, what is that? Negative 18/6 and 12/6, which means negative 3 and 2. That tells me, because it equaled the variable matrix, that tells me that, since it equals my variable matrix, tells me that x is negative 3 and y is positive 2. Good? Yeah, I know. It's not the most efficient way to solve this system of equations. You could have used substitution or regular elimination and you would have been done a whole lot quicker with it. But I just wanted to show you the process that is used because, you know what? Sometimes they use this stuff for, like, maybe cryptology. Anyway, you have fun with inverse matrices, and I'll catch you on the